Hello. In this video, we are going to combine the first and second laws of thermodynamics and thus arrive at an extremely useful result that we can use to calculate the change in internal energy that occurs as the system moves between states. Before we get on to that, however, let's first briefly review the material that has been covered in other videos. In those videos, we learned that the first law of thermodynamics introduces a thermodynamic state function called the internal energy. In addition, we are told that the change in internal energy that occurs on moving between two states is equal to the sum of the work done during the transition and the heat output during the transition. If the system is not allowed to exchange heat, work or matter with its surroundings, if the system is isolated, then the internal energy of it is fixed. The second law of thermodynamics introduces a second thermodynamic state function, the entropy. Furthermore, we are told that the entropy change that occurs as we move between two states A and B must be greater than or equal to the integral shown on the right-hand side of the expression at the bottom of this slide. In an isolated system that cannot transfer heat to its surroundings, this integral is obviously zero. We thus find that the entropy must always increase during spontaneous changes. Let's now combine these two laws. At the top of this slide, we have a statement of the first law again. The change in the internal energy of a system in moving between two states is equal to the work done plus the heat output. Remember also that the internal energy is a state function, and hence the change in internal energy that occurs in moving between two states does not depend on the path taken between the two states. Consequently, when we consider a change in state like the one shown here, we can decompose the total change in energy in terms of the change in internal energy that occurs as we move in a direction parallel to the volume axis, and then along a direction parallel to the entropy axis. We know how to calculate these two quantities, however. The change in internal energy that occurs when the volume is changed and the entropy is held fixed, i.e. without any heat transfer, can be calculated by considering how much work the system must do in expanding its volume. It is thus given by the integral over minus PdV shown here. The change in the internal energy on changing the entropy of the system without changing the volume can be calculated using the second law of thermodynamics. This is equal to the integral over TdS. We thus have that the total change in the internal energy of the system is given by the sum of these two integrals. In other words, dE is equal to TdS minus PdV. Now notice here that I keep saying the word integral, but that I have not used the integral sign at all. This is done all the time in thermodynamics. We constantly write expressions, like the one shown here, that relate infinitesimal changes in the internal energy to infinitesimal changes in the entropy and volume. We should perhaps really, however, put integral signs and limits in front of the TdS and PdV terms as shown here though. Notice also that in writing this expression, I have written the temperature and pressure as a function of the entropy and volume. This is all very nice and rigorous, but it makes our equations extremely long and ugly looking, so we generally don't do this and adopt the lazy trick of just writing these expressions with the infinitesimals instead. In deriving all these results, we have used the fact that the volume and the entropy, the extensive variables, characterize the state of the system. The pressure and temperature, meanwhile, the intensive variables, characterize the way in which the system interacts with the environment. This realization allows us to come up with a general rule. The work done, or the change in internal energy, that occurs when one of the extensive thermodynamic variables changes while holding all the other extensive variables fixed, can be calculated by taking the following integral. Here, I represents an intensive thermodynamic variable, while E is used to represent an extensive thermodynamic variable. This expression allows us to calculate how much the internal energy changes as one of the extensive thermodynamic variables is fixed. So for example, we can use this expression to calculate how much the internal energy of the system changes when the number of atoms is increased. In this case, the extensive thermodynamic variable is the number of atoms, n. The conjugate intensive thermodynamic variable to the number of atoms, meanwhile, is the chemical potential, mu. We thus have that the change in the internal energy that occurs as the number of atoms in the system is increased while holding the entropy and the volume of the system fixed can be calculated by integrating over mu dn. We can go still further, however, and also use this same mathematics and description in terms of intensive and extensive thermodynamic variables to calculate the effect that electric and magnetic fields have on the state of the system and so forth. The reason for this is that we have now uncovered a far more mathematically pleasing explanation of the difference between intensive and extensive thermodynamic variables. Extensive variables are functions of state. In other words, an extensive thermodynamic variable is a property of an equilibrated state. The intensive thermodynamic variables, meanwhile, are related to the partial derivatives of the internal energy with respect to the extensive thermodynamic variables. Hence, pressure is equal to minus the derivative of the internal energy with respect to the volume, and temperature is the derivative of the internal energy with respect to the entropy. Taking this further, chemical potential is equal to the partial derivative of the internal energy with respect to the number of atoms. Magnetic field strength, meanwhile, is equal to the derivative of the internal energy with respect to the magnetization, an extensive thermodynamic variable. We are now in a position where we can also begin to rationalize some of the ideas that we have used throughout this course and that you probably learnt early on in your scientific educations. The first of these things that we are going to look at is this business of phase equilibrium. When I talked about Gibbs phase rule and temperature, I argued that the values of the intensive thermodynamic variables have to be uniform throughout all the phases in order for these phases to be at equilibrium. We are now going to see why this is. The first thing we have to reason in doing this is that the entire two-phase system is going to be isolated, so that it cannot exchange matter, heat, or work with its surroundings. We are now going to suppose that within the system we have two phases, phase 1 and phase 2 as shown here. Furthermore, these two phases are going to be separated by a diathermal wall, which allows heat to be exchanged between the phases, but that does not allow for the exchange of matter or work. In other words, this wall is going to ensure that the number of atoms in phase 1 and phase 2 are not allowed to change. Similarly, the volumes of these two phases will not be allowed to change, so dV1 and dV2 will both be equal to 0. The entropies of these two phases will, however, be allowed to change. Furthermore, we know from what we have seen elsewhere that this process of entropy exchange will continue until the temperatures of the two phases are equal. In other words, if the temperature of phase 1 is higher than the temperature of phase 2, entropy will be transferred from phase 1 to phase 2. We can write the change in the total energy of the whole system as follows. This is equal to the change in the internal energy of phase 1, T1 multiplied by ds1, plus the change in the internal energy of phase 2, T2 multiplied by ds2. However, we know that the whole system is isolated and hence that it cannot exchange heat, work, or matter with its surroundings. The internal energy of the whole system must therefore not change. We also know, however, that if the entropy of phase 2 increases, then this must be counterbalanced by an equal and opposite decrease in the entropy of phase 1. In other words, we know that ds2 must be equal to minus ds1. This must hold because of energy conservation in the whole system. If this were not true, heat would have to be transferred out of the system, which we said is impossible because the system is isolated. We thus arrive at the following result. 0 is equal to T1 minus T2 multiplied by ds1. Now we know that ds1 is a change in entropy. ds1 therefore cannot be equal to 0, as otherwise nothing would be changing. We are thus forced to conclude that T1 and T2 must be equal, as only then will the right-hand side of this expression be equal to 0. We thus arrive at the following conclusion. If two phases can exchange some extensive quantity, then they must assume a common value for the conjugate intensive quantity. We have seen this result in a number of these videos and have frequently discussed how the intensive quantities are uniform throughout the system when it is at equilibrium. We now see, however, that this is a logical consequence of the first and second laws of thermodynamics. Before we move on, it is worth remembering that this result is only true when the system is in equilibrium with its surroundings. Obviously, there can be thermal gradients in machines and water can flow down pipes, so that there is a net transfer of material or heat from one end of the pipe to the other. These are all non-equilibrium phenomena, however. These states of the system, with thermal gradients or mass gradients, are thus being either artificially forced to be there, so the system is forced to be in a non-equilibrium state by some sort of pump, by example. Alternatively, the non-equilibrium state that the system is in is transitory and will pass once the system reaches equilibrium. Ultimately, thermodynamics tells us that we are destined to have uniform temperatures throughout the whole universe. Let's now consider something that you probably learnt long ago and that we can rationalise by considering the first and second laws of thermodynamics. Systems generally prefer to be in states for which the internal energy is minimised. In other words, balls roll down hills when they are released from a great height, and atoms and molecules are usually in their ground states. Let's now see why this is. Let's begin by supposing that the internal energy of the system varies with respect to some coordinate, something like the parabola shown here. The coordinate in question here could be the volume of the system. In addition, let's further suppose that we prepare the system so that the coordinate, the volume, has the value shown by the blue dot. In other words, the system is prepared in a state where the internal energy is not minimized. We have an energy slightly higher than the minimum. Now, our intuition about the world tells us that the system is not going to be particularly happy in this state, and that it is quickly going to relax down to the minimum in the internal energy. Let's suppose that we allow this relaxation to happen, but that we do it carefully so that we can remove all the energy that the system would output to the environment as work. In other words, the system relaxes down to the minimum in the internal energy adiabatically, i.e. in a manner that does not allow the entropy of the system to change, or that does not allow heat to be transferred between the system and the universe. Now we know that the internal energy of the whole universe must be conserved. That is to say, there is no process that can occur in the universe that allows its internal energy to change. The universe is isolated. Hence, all the work that is done on the environment as the system changes its volume must change the internal energy of the environment. It therefore stands to reason that we can transfer this internal energy back to the system in the form of heat and thereby increase the entropy of the system. Notice that in the graph I have shown here, that this transfer of entropy back into the system moves the system towards a maximum in the entropy. This is not an accident. Obviously, if the system were not moved towards a maximum in the entropy, I could run this whole process in reverse. I could transfer entropy out from the system and heat up the environment, and then return the heat output as work, thereby increasing the internal energy of the system. I thus find the following. The minimum energy compatible with a given value of the entropy is equivalent to the maximum entropy for a given value of the energy. In other words, when the system is in at equilibrium, its internal energy is minimized and its entropy is maximized. To conclude then, we have arrived at three key results by starting from the first and second laws of thermodynamics. We have shown that the state of the system is characterized by the values of the extensive thermodynamic variables, and that every extensive thermodynamic variable has a conjugate intensive thermodynamic variable, which can be calculated by taking the first partial derivative of the internal energy with respect to the extensive variable. These intensive variables characterize the way that the system interacts with its surroundings. We have then shown that if two phases can exchange some extensive thermodynamic variable, they must assume a common value for the conjugate intensive thermodynamic variable. This is in some way akin to Newton's third law in classical mechanics, and arises because if we have a two-phase system, any increase in an extensive thermodynamic variable in the first phase must be counterbalanced by a decrease in that same extensive thermodynamic variable for the second phase. Furthermore, this decrease must be of equal magnitude to the increase in the first phase. Remember that this result only holds if the two phases are in equilibrium. We can use pumps and heaters to force systems to be out of equilibrium. Furthermore, there are many physical processes that take place in the universe that are non-equilibrium phenomena and not equilibrium phenomena. The universe, in general, is not in equilibrium. Lastly, we have shown that an isolated system that is unable to exchange heat, work, or matter with its surroundings has its entropy maximized and its internal energy minimized if it is at equilibrium. This final result is hugely important because it is in many ways the start point for the statistical mechanics that we will study in the later parts of this course. Thank you for your attention.